Another continuous distribution which we often encounter is linked to the Poisson distribution, which was a discrete distribution. Assume that you have, for instance, cars arriving at some location according to a Poisson process with rate lambda. What that means is that whenever you go through one unit of time, 15 minutes, half an hour, who knows, that depends on the problem, you would expect on average there to be lambda cars that arrive within that unit of time, and the actual count of the number of cars that arrive is distributed according to a Poisson random variable with parameter lambda. Now, if instead of one unit of time you have x unit of times, so you're looking at lambda times x, the number of arrivals within x times the unit of time would still follow a Poisson process, but now its parameter would be lambda x. So we'd say something along the lines of n follows a Poisson process with parameter lambda x. Let's say that x is the wait time to the first car arrival over the lambda x period of time. And then if you're looking for the probability that you will wait more than x unit of times, that's going to be the same thing as 1 minus the probability that you will wait less than x unit of times. And what that really means is that there will have been no car that arrived in the x units of time. So, because n follows a Poisson distribution with parameter lambda x, what we have here is that the probability that n should be equal to 0, according to the PMF, right? What's the PMF for this thing? That would be, for a specific value here, would be the probability that n should be little n, which would be lambda x to the n times the exponential of minus lambda x divided by n factorial. Now we're interested in what happens when n is equal to 0, so we replace n by 0 throughout. Something to the 0 is 1, divided by 0 factorial is 1, and we end up with the exponential of minus lambda x. So the probability that you will have to wait more than x units of time for your first arrival is simply the exponential of minus lambda x, where lambda represents the Poisson parameter for the process in which cars arrive at the location. So this x here is related to the x here. The lambda sort of stands out on its own. We'll say that x follows an exponential distribution, exp lambda. We'll say it as x. If its cumulative distribution function is 0 for x smaller than 0 and 1 minus e to the minus lambda x for every other value of x. In particular, because the probability density function is the derivative of the cumulative distribution function, well, you differentiate both of these branches. The first branch, which was originally 0, differentiates to 0, and the second branch, which was originally 1 minus e to the minus lambda x, now becomes lambda e to the minus lambda x. This is a probability density function because the integral of this function over the real line is indeed equal to 1. You'll have to compute it. Here's an example. Perhaps lambda is equal to 4. Then we have x follows an exponential distribution with parameter 4. This curve here, 4 times e minus 4x, and the probability, for instance, that x is smaller than 1 over 2 would be the area between 0 and 0.5. The corresponding cumulative distribution function would be 0 before 0, then 1 minus lambda e to the minus lambda x. That's not true. The commutative distribution function would be 0 leading up to 0, and then 1 minus e to the minus lambda x the rest of the way. So the value that we had found here for the area under the curve between 0 and 0.5, this height here, was about 86.5%. Here's this number. The exponential distribution being linked to the Poisson distribution has properties that are at least linked as well to the properties of the Poisson distribution. In particular, the expectation of an exponential random variable is 1 over lambda, and the variance is 1 over lambda squared. It has one very important property: it is memoryless. Let's say that x is meant to represent the wait time again, like in the previous example, the amount of time you wait before the first car arrives. What the memoryless property is saying is that the probability that you would have to wait in total s plus t units of time, given that you've already waited t units of time, that's just the probability that you would wait more than s units of time. This exponential random variable is the continuous analog of the geometric distribution, GOP, which was basically counting the number of trials until a success occurred. While here we're measuring the amount of time before an event occurs. As an example, let's say that the lifetime of a type of light bulb is exponentially distributed with mean 100 hours. That means that lambda, in this case, would be 1 over 100. Remember, the exponential distribution has an expectation of 1 over lambda. If this is equal to 100, then obviously lambda is equal to 1 over 100. What's the probability that a light bulb will last at least 100 hours? Well, we know here that this wait time until the light bulb stops working, that the event that it stops working, is supposed to follow an exponential distribution with 1 over 100 as the parameter. So the probability that x would be greater than 100, that would be 1 minus the probability that x is smaller than or equal to 100, and we can just plug in the values here. And we will get, using the commutative distribution function, that this probability is going to be the exponential of minus 100 over 100, which is to say e to the minus 1, about 36.8%. Now, we don't know if it makes sense that light bulbs have lifetimes that are exponentially distributed, but if they do, about 36.8% of them would last more than 100 hours, which would mean that about 63% of them, roughly speaking, would last fewer than 100 hours. But the distribution here isn't symmetrical. Now, if you know that a light bulb has already been burning for 100 hours, what's the probability that it will last at least 100 hours more? This is where the memoryless property comes in. You're trying to figure out the probability that it will last more than 200 hours, given that it has originally already lasted more than 100 hours. So the memoryless property says that this would be the same as the probability that it will last more than 100 hours. Right? Here s is equal to 100, t is equal to 100. It doesn't matter that it's already lived 100 hours, according to this memoryless property. The probability that it will last for 200 hours, given that it's already lasted 100 hours, will be the same as the probability that it lasts 100 hours to start with. Now, we know that that's probably not true of light bulbs in general. So that provides some evidence to suggest that the lifetime of light bulbs is probably not exponentially distributed. But let's assume that it was exponentially distributed. Now the manufacturer would like to guarantee that their light bulbs will last at least T hours. What that means is that we're looking for the value T, which will satisfy this expression. And we know that this expression, the probability that x will be greater than t, that's the same thing as 1 minus the probability that x will be smaller than or equal to t. And we know what this is. This is the cumulative distribution function. This is f of t. Now we know what 1 minus f of t will be. We have an expression for f of t. We saw it a few slides back, right here. So we have 1 minus this, where x is actually given as t. And that becomes the exponential of minus 0.01 t, because our lambda, if you remember, was 1 over 100. So we're trying to find the value of t, which solves 0.9 equal e to the minus 0.01 t. Now you solve it taking logarithms on both sides, and there's only one such value. T has to be equal to 10.5 hours. So if you want to guarantee, find a threshold that would allow the manufacturer to say 90% of the light bulbs last longer than this amount of hours, well, that amount of hours has to be 10.5. Not a great number of hours for light bulbs in general.